Let's talk about the epsilon delta definition of continuity. So this blue strip here is representing how close we want our outputs to be to a given value. And you can see that if we make our inputs really close to 2, this strip is going to lay entirely in that blue region. Let's watch it one more time. So we want to get our outputs in that blue region, and we can see if we make our horizontal strip small enough, then we're going to achieve that. And we can achieve that even if we zoom in and make that epsilon strip, that blue strip, really narrow. So this is day 21 in our series Let's Learn Real Analysis on TikTok. And today we're going to talk about formally what is this delta epsilon definition of continuity. So it's on the screen here, but it captures what we just saw in the video, which is that if our inputs are really close to a value a, then the output should be really close to f of a, the function value at that point. Now I want to call attention, this is similar to other definitions we've had before, where we have to show something is true for all epsilon. We have to construct something. In this case, we have to construct a delta such that an if-then statement is true. Let's see how this would work in a proof. So let's try and prove that the function x cubed is continuous at x equals 2. So we're going to start our proof with letting epsilon be arbitrary and positive. And we're not sure what we're going to have to define delta to be equal to. And in this proof, we may need more calculations. But what we're going to do is we're going to assume that our inputs x are pretty close to 2. And we're going to try and show that our outputs are going to be pretty close to 8. And so we do some algebraic simplifications, and what we notice after we factor is we get this factor of x minus 2 in absolute value, which of course is going to be strictly less than delta. And so now the question is, what do we do with this extra factor here? Well, that extra factor is some number. Maybe we can try and analyze it. So the key to unlocking these sorts of proofs is to realize that you are in charge of picking delta. And if you want to say that delta is going to be smaller than 1, well, you're right, you can do that. And what that tells us is then x is guaranteed to be within a distance of 1 from 2, and so that means that x has got to be sandwiched between 1 and 3. And now if you think about the ramifications of that, well, that means x squared is between 1 and 9, and when you work out x squared plus 2x plus 4, you see that it's between 7 and 19. And that allows us to use that information later in our proof when we got to that pesky quadratic term and absolute values. And so now to finish the proof, well, now we can go back and define our delta way up here and say, you know what, I'm going to make sure it's less than or equal to 1. And also I want to make sure it's less than or equal to epsilon over 19, because I know when I put the whole proof together, I'm going to be getting delta times 19, and I want to make sure that's less than or equal to epsilon. I really like these proofs because you get to see how creative one can be in mathematics, in defining delta, in putting all the pieces together, and trying to work backwards. I think this is a perfect example.